Welcome to This Explainer. You know, we interact with steel literally every single day, from our kitchen appliances to the bridges we drive on. But there's an entire invisible universe operating right under our fingertips that totally dictates how these materials behave.
Section 1. The Magnetic Mystery. Let's kick things off with a physical paradox that honestly stumps a lot of people until they look at the atomic level.
So here's the core mystery we're exploring today. If you take two seemingly identical pieces of steel, a simple magnet might aggressively snap and stick to one of them, right? But then it completely ignores the other. It'll just slide right off as if the metal was made of plastic or wood.
Now, the plot thickens here. Both of these metals are fully capable of conducting an electrical current perfectly. They're steel, they've got metallic properties, and electricity flows through them without a hitch. This shared electrical conductivity makes the magnetic difference even more puzzling. Why does the physics of magnetism fail where the physics of electricity succeed?
Section 2. Ferrite versus Austenite. To actually figure this out, we need to look at two different crystalline structures that steel can take on. Just to make sure we're on the exact same page, let's quickly nail down our terms. When we say something is ferromagnetic, we mean it's strongly attracted to magnets. And non-magnetic, well, it is exactly what it sounds like. It's totally unresponsive to a magnetic field. Looking at the materials themselves, the divide is super clear. Ferrite, which covers your common carbon steel and ferritic stainless, is highly ferromagnetic. Put a magnet near it, bam, it grabs hold. On the flip side, austenite, specifically austenitic stainless steel, it completely ignores the magnet. Totally non-magnetic.
So, the million-dollar question. If they're fundamentally the same base material, iron-based steel, and they both conduct electricity like a charm, why on earth is one strongly ferromagnetic and the other just not?
Section 3. The empty center. To solve this, we gotta zoom way into the microscopic atomic level.
Because the secret here doesn't actually lie in the chemical makeup. It's all about the physical, geometric arrangement of the atoms themselves. Specifically, what's going on right dead in the center of their atomic grid. And the structural difference is wild. In the ferrite structure, the atom in the very center is fully connected to all the surrounding atoms. It forms this solid, continuous network. But austenite is radically different. In austenite, the microscopic center is just missing. It's completely empty. And we're not talking about some tiny negligible gap here. According to the data, a massive 41% of the austenite atomic structure is essentially empty space. Imagine that. Almost half of the structure right at the center is just a void.
When you actually visualize that 41% void, you realize just how porous and open austenite is on a microscopic level. It's kind of like looking at a massive skyscraper where the entire central elevator core is just totally gone.
Section 4. Broken magnetic fields. Let's see how this exact percentage of empty space actively messes with the physics.
Here's how it plays out in practice. Electrical currents, which are just electrons flowing along the metallic framework, have no problem navigating the perimeter because the outer frame of the atoms is still connected in austenite. Electricity just flows right around that empty center. But magnetic fields, they don't work like that. They have to pass straight through the center of the structure. And when they hit that 41% empty space, the void literally severs the magnetic field lines. They just can't cross the gap. So it all comes down to connectivity. Ferrite acts as a solid, continuous bridge for magnetism. The field lines travel straight through that connected center atom without a hitch. Austenite, though, acts like a collapsed bridge. The path is broken. The empty space causes the magnetic field lines to disconnect and fail, which completely explains why the magnet simply falls right off the metal.
Section 5. The field test. Let's look at how industry pros turn this microscopic physics lesson into an everyday superpower.
Out in the field, whether you're in construction or engineering, workers obviously don't have the time to put metal under an electron microscope. So they use a simple magnet as a brilliant life hack. Got an unknown piece of steel? Just place a magnet against it. If it sticks, you instantly know the invisible atomic structure is solid and connected. It's ferrite. If it doesn't stick, you know a massive 41% of its microscopic center is empty space. It's austenite.
It's honestly amazing to recap this and see how two metals that both conduct electricity flawlessly can have such vastly different magnetic properties. And it's entirely dictated by whether their microscopic center is connected or completely empty.
The ultimate takeaway here is how incredibly useful this invisible structure is. You don't need a PhD in physics to harness this knowledge. Just by carrying a small magnet in your pocket, you can instantly classify and understand the fundamental nature of the steel you're working with on the fly.
So the next time you interact with a metal surface, whether it's your kitchen sink or a steel handrail, remember that the invisible, empty spaces hiding deep inside are actively dictating the physical reality you experience on the outside. Ask yourself, are you touching a solid atomic bridge or a microscopic void? Thanks for tuning into this explainer, and keep questioning what's under the surface.